What if chips powering today's AI revolution aren't the chips that will define the future of intelligence? Right now, AI models that write, see, plan, and predict are powered by specialized silicon, GPUs, TPUs, and custom accelerators designed for one thing: matrix math at massive scale. They feel unstoppable. But in labs running colder than the outer space, scientists are building machines that don't calculate step by step at all. They operate on a probability, superposition, and entanglement, the most unintuitive rules of nature. So today we are asking a bigger question. Is the future of intelligence built on a better silicon or entirely different physics? Welcome back to Chips Weekly by Diana, where we decode the hardware beneath the headlines. This episode isn't about which chip is faster, it's about how the computation itself is changing. One path stretches classical computing to its absolute limits, the other abandons classical rules entirely. AI chips versus the quantum chips. Engineer mastery versus the fundamental physics, and why the real future belongs to those who understand both. AI chips are not general-purpose computers. They're purpose-built machines designed to do one thing exceptionally well: move and multiply enormous amount of data as efficiently as the physics allow. Modern AI models are built on vast layers of linear algebra. Every image, word, or decision becomes a stream of vectors flowing through the matrices. AI chips are designed around this reality, placing massive numbers of simple compute units as close as possible to extremely fast memory. That's why today, leading AI processors look enormous. Not because they're always a single giant piece of silicon, but because they assemble large amounts of silicon into one logical system. Multiple compute dies, stacked high bandwidth memory, and advanced interconnects are packaged together so that data travels the shortest possible distance. At this scale, architecture matters more than the transistor size itself. Most of the energy is no longer spent on mass, it's spent moving the data. So chip designers fight distance, latency, and power loss with the chiplets, 3D stacking, and advanced packaging techniques that turn many components into what behaves like one massive processor. This approach has powered the AI boom, but it reveals also the limits of classical scaling. Power density keeps rising, cooling becomes harder, and costs climb faster than the performance. AI chips dominate today not because they're perfect, but because they represent the most efficient classical architecture we know how to build. Classical computing, including AI chips, is still bound to deterministic logic. Each operation produces one correct output. Each transistor switches between on and off. Every computation marches toward step by step, even when massively parallel. That works well until problems explode exponentially. Molecular interactions, protein folding, global optimization problem, cryptographic factorization. The number of possible states grow faster than any classical machine can track. That's where scaling stopped working. And this is where the quantum helps. Quantum computers don't store answers. They store probability distributions. A qubit isn't 0 or 1. It's a weighted combination of both. When many qubits interact, the system represents an exponential number of states at once. The power comes from the inference. Correct solutions are amplified. Incorrect ones cancel out. When a quantum algorithm works, it doesn't check every answer. It reshapes the probability landscape so that the right answer becomes inevitable. That's why quantum computing is so powerful and so narrow. It excels at problems where the nature itself is quantum. Chemistry, materials, physics, optimization landscapes with massive state spaces. But quantum hardware is brutally hard. Superconducting qubits require millikelvin temperatures. Ion traps demand extreme precision. Photonic systems fight loss and noise. Error correction can require thousands of physical qubits for one usable logic qubit. Quantum computers are not weak. They are unfinished. Here's a mistake most people make. They imagine quantum computing replacing AI chips. That won't happen. Quantum machines are terrible at perception, language, and real-time interaction. They don't run neural networks efficiently. That they don't scale cheaply. AI chips will remain the front end of intelligence. But quantum chips will become the back end. AI will propose hypotheses, generate candidates, explore solution spaces, and learn from data. Quantum processors will solve the hardest inner loops, molecular simulations, optimization bottlenecks, and cryptographic challenges. AI will ask the questions, quantum will answer the ones classical machines cannot. Together they form a new computing stack, one that spans classical logic and quantum probability. So the real space isn't just about the technology, it's about who controls the integration. The United States dominate AI, silicon, and software ecosystems. China excels at large-scale AI deployment and infrastructure. Europe leads in quantum materials and physics. Japan and Canada push quantum algorithms forward. But the decisive advantage won't come from building the best quantum chip. It will come from building the best hybrid systems, tightly integrating quantum accelerating into AI workflows, cloud platforms, and national infrastructure. The first country to make quantum computing useful, not just impressive, will shape the next era of intelligence. So here's the real question. Is the future of computing about pushing silicon further or about embracing entirely new physics? Or is the real answer learning how to combine both? Let me know what you think. And if this special edition of Chips Weekly by Diana helped you see the future more clearly, so then like, subscribe, and share it with someone who wants to understand what's coming next. Until next time, stay curious, stay sharp, and stay chip aware.